Welcome to the video lecture on the subject Computer Vision, Unit 4, 3D Reconstruction, Part 5. I am Dr. K. Padmapriya, Assistant Professor, Department of ECE, Government College of Engineering, Tirunelveli. Probabilistic models. Sophisticated probabilistic inference techniques are often used to estimate the likely states of the person being tracked. Particle filtering was developed for tracking the outlines of people, and hands was subsequently applied to the whole body tracking and continues to be used in modern trackers. Alternative approaches to handling the uncertainty inherent in tracking, including multiple hypothesis tracking and inflated covariances. And the figure shows a sophisticated spatio-temporal probabilistic graphical model called loose-limbed people, which models not only the geometric relationship between various limbs but also their likely temporal dynamics. The conditional probabilities relating various limbs and time instances are learned from training data, and particle filtering is used to perform the final pose inference. Another essential component of whole body modeling and tracking is the fitting of parameterized shape models to visual data. The availability of large numbers of registered 3D range scans can be used to create morphable models of shape and appearance. A sophisticated system called SCAPE, which is shape completion and animation for people, which first acquires a large number of range scans of different people in varied poses and then registers these scans using semi-automated marker placement. The registered data sets are used to model the variation in shape as a function of personal characteristics and skeletal pose. Example, the bulging of muscles as certain joints are flexed. The figure shows the estimating of human shape and pose from a single image using a parametric 3D model. A training shape database, and this is the model, parametric 3D model SCAPE. So from a single image, initialize the points and fix up the pose, and to that optimization is made. So adding up with the model, and from the real-time picture, this will how edges, shading are obtained, and then the output is imposed over the model, that is 3D pose and shape model. And doing the animations, it can made with used for different applications, and caricature measurements will be made from it. This is how the human shape and pose is made from a single image using a parametric 3D model. The resulting system can then be used for shape completion, that is the recovery of a full 3D mesh model from a small number of captured markers by finding the best model parameters in both shape and pose space that fit the measured data. Because it is constructed completely from the scans of people in close-fitting clothing and uses a parametric shape model, the SCAPE system cannot cope up with the people who are wearing the loose-fitting clothing. So this limitation is overcome by estimating the body shape that fits within the visual hull of the same person observed in multiple poses. An initial surface mesh fitted is adapted with the parametric shape model to better match the visual hull. This picture shows a whole body expression and the gesture fitting from the single image using the SMPLX model. So estimating the major joints from this single picture. So these are the major points, and then the skeleton from these points, and then the SMPL and SMPL-X models for this single image. And the figure B, it shows the qualitative results of a SMPL-X model for some in the wild images. So all these are the images, and from this, these are the final simple X models. Like this, these are the models which have been recreated from this single picture. Next is the activity recognition, the final topic in the human modeling. Is motion, activity and action recognition. So examples of actions that are commonly recognized including walking, running, jumping, dancing, picking up objects, sitting down and standing up, and waving, etc. Recovering the texture maps and albedos. After a 3D model of an object or person has been acquired, the final step in modeling is used to recover a texture map to describe the object's surface appearance. This first requires establishing a parameterization for the u, v texture coordinates as a function of 3D surface position. One simple way to do this is to associate a separate texture map with each triangle or pair of triangles. More space-efficient techniques involve unwrapping the surface onto one or more maps. Example, using a subdivision mesh or a geometry image. Once the u, v coordinates for each triangle have been fixed, the perspective projection equations mapping from the texture u, v to an image j's pixel uj, vj. So this is a general representation and this is the pixel coordinates for the particular image j. And this can be obtained by concatenating the affine u, v which is leading to the xyz mapping with the perspective homography xyz to uj, vj. The color values for the u, v texture map can then be resampled and stored, or the original image can itself be used as the texture source using projective texture mapping. The situation becomes more involved when more than one source image is available for the appearance recovery, which is the usual case. Use a view-dependent texture map in which a different source image or a combination of source images are used for each polygonal face based on the angles between the virtual camera, the surface normals and the source images. An alternative approach is to estimate a complete surface light field for each surface point. When using models in traditional 3D games, it is preferable to merge all of the source images into a single coherent texture map during the pre-processing. Ideally, each surface triangle should select the source image where it is seen most directly and at the resolution best matching the texture map resolution. This can be posed as a graph cut optimization problem, where the smoothness term encourages adjacent triangles to use similar source images followed by blending to compensate for exposure differences. Even better results can be obtained by explicitly modeling geometric and photometric misalignments between the source images. Neural texture map representations can also be used as an alternative to RGB color fields. The figure shows the estimation with the diffuse albedo and reflectance parameters for a scanned 3D model. This shows a set of input images projected onto the model this shows the complete diffuse reflection albedo model, and the part C shows rendering from the reflectance model including the specular component. These kinds of approaches produce good results when the lighting stays fixed with respect to the object. That is, when the camera moves around the object or space. When the lighting is strongly directional, however, and the object is being moved relative to this lighting, strong shading effects or specularities may be present, which will interfere with the reliable recovery of a texture map, that is the albedo map. In this case, it is preferable to explicitly undo the shading effects by modeling the light source directions and estimating the surface reflectance properties while recovering the texture map. And a figure shows the results of one such approach where the specularities are first removed while estimating the matte reflectance component, that is the albedo, and then later reintroduced by estimating the specular component Ks in a Torrance Sparrow reflection model. Estimating BRDFs. So BRDFs means bidirectional reflectance distribution function. A more ambitious approach to the problem of view-dependent appearance modeling is to estimate a general bidirectional reflectance distribution function, that is a BRDF function, for each point on an object surface. Different techniques are used for estimating these BRDF functions, while few of them provide surveys of BRDF modeling, recovery and rendering. The BRDF can be written as a function fr of theta I, phi I, theta r, phi r, lambda, where the theta I and theta r, phi r are the angles of the incident light Vi cap and the reflected light Vr cap light ray directions, which make with the local surface coordinate frame dx cap, dy cap, comma, n cap. When modeling the appearance of an object as opposed to the appearance of a patch of material, we need to estimate this function at every point x, y on this object surface, which gives us the spatially varying BRDF or SV BRDF. So, which will be a function of, mentioned as FV, of x, y, theta I, phi I, theta r, phi r. These are for the incident lights, and these two parameters are for the reflected light, lambda. If subsurface scattering effects are being modeled, such as the long range transmission of light through materials such as alabaster, then the 8-dimensional bidirectional scattering surface reflectance distribution function, that is BSSRDF, is used instead. So it is represented as a function of Fe, which will be a function of xi, yi, theta I, phi I, xe, ye, theta e, phi e, where this e subscript will now represent the emitted rather than the reflected. So in the earlier case, it was the incident and reflected light parameters. Here it is the emitted light which will be analyzed instead of the reflected light directions. So basic photometry BRDF models traditional BRDF acquisition using gonio-reflectrometry, that is the precise measurement of visual angles and reflectances, multiplexed illumination, skin modeling and image-based acquisition techniques which simultaneously recover an object's 3D shape and reflectometry from multiple photographs, estimate locally varying BRDFs and refine their shape models using the local estimates of a surface normal. To build up the models, first associate a lumitexel which contains a 3D position, a surface normal and a set of sparse radiance samples with each surface point. Next, cluster such lumitexels into materials that share common properties, like using a Lafortune reflectance model and a divisive clustering approach, and then finally to model detailed spatially varying appearance. Each lumitexel is projected onto the basis of clustered appearance models, which is shown in this picture. That is, this is the image based reconstruction of appearance and detailed geometry. So first pictures are the appearance models, that is the BRDFs, which are re-estimated using divisive clustering, and the part is to model detailed spatially varying appearances. Each lumitexel is projected onto the basis formed by the clustered materials. A more accurate system for estimating the normals can be obtained using polarized lighting. To recover spatially varying BRDFs, that is SPBRDFs, either start with RGBD scanners, flash or no flash image pairs, or use the deep learning approaches to simultaneously estimate the surface normals and the appearance models. Certain systems can estimate shape and environmental lighting from range scanner sequences or single monocular images, and even perform relighting on such scenes, capturing the 3D shape and appearance of objects with the RGBD cameras. While most of the techniques require large number of views to estimate the surface properties, an interesting challenge is to take these techniques out of the lab and into the real world, and to combine them with regular and internet photo image based modeling approaches. Application in one of the application is 3D model capture. The techniques for building complete 3D models from multiple images and then recovering their surface appearance have opened up a whole new range of applications that often go under the name 3D photography. The processing steps of feature matching, structure from motion recovery, dense depth map estimation, 3D model building, and texture map recovery are performed. A complete web-based system for automatically performing all of these tasks is called ARC3D. ARC3D. A more recent commercial photogrammetric modeling system used for both object and screen capturing is Pix4D, whose website shows a wonderful example of a 3D textured map castle. This is the castle, which is reconstructed from both the regular and aerial drone photographs. Example of casual 3D photography is enabled by advent of smartphones. An alternative to such fully automated systems is to put the user in the loop in what is sometimes called interactive computer vision. Example, facade architectural modeling system. Video trace system, which performs the automated point tracking and 3D structure recovery from video, and then lets the user draw triangles and surfaces on top of the resulting point cloud, as well as interactively adjusting the locations of model vertices. A related system that uses matched vanishing points in multiple images to infer 3D line orientations and plane normals These are then used to guide the user drawing axis aligned planes, which are automatically fitted to the recovered 3D point cloud. Fully automated variants on these ideas, the improvement in sophistication and reliability, we can expect even more user-friendly applications for photorealistic 3D modeling from images. This is the end of the part 5 of the video.